Hello, Max. Hello. Hey, guys. So last week's homework, I think I made it a little too challenging. So hopefully if you had any trouble, then the solutions cleared up some of the confusion. Um, this week we'll tone it down a little bit. It's not going to be any new stuff. It's going to be um, more like applications of all we've learned so far. So it's going to be an easier class this week. Hello. Something's ringing back there. It's 8 o'clock. For me, at least, it's 8 o'clock. I'm going to share my screen. So maybe I'll wait a little bit more for the people to come in. So we've got one more week until school starts, at least for me, one more week of summer. For this class, we've got 4 more weeks, I think, including this week. All right. So how about I get started now? So this week is week 15, and we're doing statics, elasticity, and fracture. So those are the 3 main things we're going to be doing. And the bulk of the class is going to be about statics. And then in the end, we're going to go briefly over elasticity and fracture. Okay, so let's get started. So once again, the topics are statics, types of equilibrium, elasticity, and fracture. So those are the 4 topics for today. So let's start off with statics. So you may ask, what even is statics? Well, if you see in the word static, what does the word static mean? Static means unchanging. And in physics, statics is what we do with things that are not moving when, like per the definition of the word static. In statics, we basically analyze all of the physics behind why something doesn't move. So an easy example is a box hanging from a string on the ceiling, right? If this box isn't moving and we analyze why this box doesn't move, then we're basically analyzing statics here. So statics is the physics behind any object that doesn't move, okay? So since the definition of this is so simple, and it seems like we've done a lot of problems similar to this before, so it's going to be pretty easy for you, I think. and we're just going to go more in depth about it. Okay, so statics is basically the physics behind anything that's not moving, stable. Okay, and in statics we have something called static equilibrium. Okay, so that's called static equilibrium, and static equilibrium is basically a fancier word to describe an object at rest, or yeah, like that. So static equilibrium is just describing an object at rest. So if an object isn't moving, we would say that this object is in static equilibrium. So things that are in static equilibrium are things that aren't moving. Okay? So what qualifies something as being in static equilibrium? So there are actually two qualifications that are needed. The first qualification is no net force acting on the object. And the second qualification is no net torque. Okay, so these are pretty intuitive, right? If there was a net force on the object, then it would start to move and it would flip over or whatever, right? And wouldn't be in static equilibrium anymore. So that's why there cannot be any net force. And also there can't be any net torque on the object because then the object would start spinning or rotating, and then it wouldn't be in static equilibrium either. So these are the two things we need for static equilibrium. First, no net force is allowed and no net torque is allowed. Okay, so the basic problem-solving procedure you would use for solving things in static equilibrium is that you basically have two things here. And first, you can look at no net force, this part, no net force. Like, what kind of equation can you make out of no net force? Well, F equals ma. And if the thing is in static equilibrium, then A must be 0. So the sum of all the forces on the object must equal 0. So 0 equals force 1 plus force 2, etc. Okay? So that's one equation you can get from the definition of static equilibrium. All the forces must balance out somehow. And similarly for no net torque, 0 must equal to torque 1 plus torque 2 plus torque 3. Now you've basically got two equations you can use for force, for static equilibrium, okay? So once you have these two equations, you can then solve for what you need, okay? And one extra thing to note about torque is that when we analyze torques on an object at rest, let me give you an example of a ladder resting against a wall. We're going to see a problem like this later on. So let me give you the example of a ladder resting against a wall, right? It's in static equilibrium. So when we say no net torque, how do we figure out what the torque is, right? Torque depends on where we decide our pivot point. If the pivot point is here, then torque is different than if we were to decide our pivot point is there, right? That's what you basically think, right? Because torque equals force times radius, right? So if we put our pivot point at the bottom here, then the radius would be different if we had put the pivot point in the middle of the ladder, right? So how do we go about solving if the torques are different around each pivot point? Well, even though the torques may be different, the thing is that it doesn't matter. It actually doesn't matter what you choose as your pivot point, okay? If the object is in static equilibrium, it shouldn't matter the point that you choose for your torque, your pivot point, right? So the thing is, for no net torque, you can choose any pivot point. You can choose any point along the ladder as your designated pivot point. And no matter what point you choose, the torques will always balance out to equal to 0, no matter what. The torques will all sum up to 0, even though the torques themselves are individually different, okay? So if we choose different pivot points, then each torque will be different, but overall, they will still add to 0. So the basic conclusion you can get from this is that when we analyze torque on an object in static equilibrium, you can choose any point along the ladder, for example, as your pivot point, and then you can analyze torques about that point. Okay, it doesn't matter which point you choose, it will all work out. Okay, so those are basically the things you'll know for static equilibrium, right? You get these two equations, and then you solve for what you need. Okay, Are there any questions? Okay, so as you may see, as you have seen, this week is actually not that hard, right? You know all these things, you know how to do these, so it shouldn't be that hard. Okay, it's gonna be an easier class today. All right, I have this example problem for you to basically show you how to do a problem involving statics. So we have a chandelier in the image, and it's at static equilibrium. Okay, so what's the tension in each cable? We have one cable here, one cable, and one cable. So we have 3 cables. What's the tension in each cable? Well, first of all, the easiest thing to do is that if we look at the chandelier, there's mg pulling it down, and then let's say this is T1, right? The only thing that's supporting the chandelier is that rope. So T1 must equal to mg, right? That's pretty easy. And then how do we figure out the tension here and here? They're not connected to the chandelier. So how do we figure out that? Well, let's analyze the point here where all 3 of the strings meet together. Let's look at this point right here. Let me draw it out here. So we have one tension going this way. Let's say this is T2. We have T3. And as we know, tensions, they go towards the center of the string. So tension in here, in the first string, it goes like that. It goes together. So we do have T1 pulling down right here. So now we have this diagram of the specific point where all 3 cables meet. And if the whole thing is in static equilibrium, this point must also be in static equilibrium. So all these tensions must balance out. Okay? So what I would do is divide up the tensions into their own components, right? Because we can't really do analysis if the T2 is at an angle. Okay? So basically, we're going to divide T2 into its components. So this way, it's going to be T2 cosine 60, and this way, T2 sine of 60. See this triangle right here. Okay, so that's how I got it. So now that we've divided T2 into its components, now we do the force analysis. All the forces on the y direction have to balance out. They all have to sum to 0. So T2 cosine 60 minus T1 equals 0, right? Because these forces have to balance out. Otherwise, the object would not be in static equilibrium. Similarly, for the horizontal direction, we have these 2 forces. So T2 sine of 60 minus T3 equals 0 as well. Now we've got 3 equations and 3 unknowns. T2, T1, and T3. 3 equations, 3 unknowns. Now we can solve for what we need. Okay? So now let me get rid of this. And we'll solve these problems. So first of all, we know T1 is mg. We could already find that. And if we substitute T1 in as mg right here, then we got T2 cosine 60 equals mg. T2 equals mg over cosine 60. Okay, so that's T2. Now we know what T2 is. We can plug it in here. So mg sine 60 over cosine 60 minus T3 equals 0. So T3 equals mg tangent 60. Right? If you do sine 60 over cosine 60, that is the tangent of 60. Okay, so if you were to plug values in here, you would get your answer. All right, so that's how you would do a statics problem. It's not that complicated. Okay, and you may ask, why did I only do force here? I didn't write any kind of torque in this problem. And the thing is, sometimes you don't need to do both torque and force. You don't need to make both equations. Okay? Sometimes if you just analyze the force, it will give you your answer right off the bat. Okay? So if just an analyzing force gives you your answer already, then you don't need to do any more calculations. You already have your answer, right? So you can just go with it. But some of the time, just doing a force analysis will not give you all the answers you need. And maybe you'll have 2 variables and only 1 equation. So then you would have to make an extra equation using torque. Okay? But sometimes, most of the time actually, you really only need to do either a calculation in force or a calculation in torque. It depends on which one you choose. Okay? Are there any questions?
In which cases will you need to use both?
So sometimes when you just do force, sometimes you get an equation like T1 plus T2 equals 60 or something like that. That's all you get from the force analysis. In like a theoretical question, you would just guess this equation, right? If you just have this equation, you still don't know what T1 and T2 are. So then you would use torque to make an additional equation that you can use to solve for each of those things. So basically, sometimes you only need one equation, but when you don't have enough information, just by analyzing force, you will need to analyze torque along with it to get more information. Okay, does that answer your question?
Mm-hmm.
Cool. 3 problems here. 2 of them are conceptual. So I'll give you guys maybe about 3 minutes for these. Okay? You got your answer, please chat that to me. And I'll let you know if you're right or not. Actually, I just noticed that on the last example, I actually made a mistake when I looked at the right triangle here. I said this was sine of 20 and this was cosine of 20. But if you actually look at the triangle and you take this out like this and you kind of flip it over, it will look like this. So obviously this is sine of 20. This is cosine of 20. So that means I actually made a mistake there. So up direction is the sine of 20. This direction is the cosine of 20. Okay? So these triangles are often tricky if they're drawn weirdly like that. So you always have to be careful. It's very easy to make mistakes in that way. All right, I'm going to explain these now. So one example where the net force on an object is 0, but it's not in static equilibrium, well, then there must be some kind of net torque acting on the object, even though the force is 0. So one example would be if I had a cylinder lying flat on the table, like a plate, for example. If I were to apply a force like this, well, actually, if I were to apply a force like this, the net force is 0 because the forces are going in opposite directions, but these forces both exert torque, which will make the table spin. For a second example, net torque is 0, but it's not a static equilibrium. Then if we apply forces this way, net torque is 0 because these forces balance out, but the net force is not, and the object will accelerate this way. Okay. So now for the third question. Now you basically do what I did in the example problem, right? So obviously the first one is tension C. Tension C must equal to mg, otherwise the box would fall, right? So now let's analyze the point right here. There's tension A going out like this, tension B, tension C pulling down. Okay, so tension C equals mg. And before we do anything else, we need to divide tension A into its components. So this way is tension A sine of 20. This way is TA cosine of 20. Okay, so what do we have now? So the vertical forces must balance out. So TA sine of theta equals to TC. And horizontal forces also balance out. So TA cosine 20 equals TB. And then we would just substitute TC in as mg. So then TA equals mg over sine of 20. TB, we just substitute TA into this equation. So then we get mg over the tangent of 20 equals TB. Okay, does everyone understand this? So I'm not going to evaluate what this exactly is, but I hope you guys get the idea. All right. So now we have a different problem with static equilibrium. I'll give you, shouldn't be too hard, so I'll give you 2 minutes for this one. And when you get your answer, please chat that to me. Drop something. All right, I'm going to explain this one now. So 2 children sit on a seesaw and it's in static equilibrium. So we can get 2 equations. We can get a force equation or a torque equation. And we kind of want to be strategic with this because if we choose the right equation to make in the first place, and it gives us enough information to just solve it without using the other equation, then we'll just save a lot of time, right? So we got to systematically choose which method we use first, okay? So do we do torque or do we do force here? Well, intuitively, it seems like we should do torque, right? Because the seesaw will spin. So let's just analyze torque. So I said that you can choose any pivot point as your reference frame, okay? So which pivot point do I use? Well, in this case, it's actually the easiest to just choose your pivot point as the point at the hinge, right? Because you already have the distance of the 30 kilogram kid, and you have to compare the distance of the 25 kilogram kid to that point. So that's the point we're going to use to analyze our torque. So what are the net torques about this point? Well, there is the 30 kilogram going down. There's the 25 kilogram going down. And we can't forget about the mass of the board, the mass of the seesaw. The mass is going straight through the center. Okay? So the net torque must equal 0. 0 equals, let's do torques in this direction as positive, torques in this direction as negative. So then we got 30 times G times R. This is 2.5. And then 2.5, 25 kilogram is in the other direction, minus 25 times G times X. And then the 2 kilogram mass, the gravity force, it goes straight through the center, which means R equals 0. So there's no torque acting on the center based on the mass of the seesaw. Okay, so that's all the torque we have. So now let's solve. 30 G times 2.5 equals 25 G times X. Cancel some G's. We'll get X equals 3 meters. All right. Are there any questions?
In what case would the mass of the seesaw matter instead of being canceled out as it is now?
So the seesaw, the seesaw is perfectly balanced on the hinge. When you go to a seesaw, it's perfect. The middle of the seesaw is right on the hinge. If in some case you were to have a hinge here, but the seesaw is like slightly displaced away from it, then the center of mass would be exerting the torque. Okay, so that's when you would consider the mass of the seesaw for your torque equation. Okay, another problem here. So the thing with static problems is that you have to go through a lot of problems, and these are actually pretty common problems. These are basically the standard problems you're going to be tested on. So if you are familiar with doing each of them, then they'll be pretty easy for you when you if you encounter them on a test or something. So I give you guys 3 minutes for this one. All right, I'm going to go ahead and explain this one now. So we have a beam placed on 2 support poles and a 150 kilogram point mass right here. It's put on the board, and then we want to find out what are the forces exerted by each of the poles. Okay, so first of all, I see forces, so I'm going to think, let's just start out with a force equation, right? So the force equation would be, we got to analyze all the forces on this diagram. So let me first draw them out. We have M of the beam. We have the M of the point mass. And then we have the 2 forces, and I think that is it, okay? So those are all the forces. So this means that the forces have to balance out. So FA plus FB equal MBG plus MPG. And that's basically the only equation we get. And as Fiona mentioned earlier, when do we ever need to use 2? Well, right here, you can see that the force equation gives us one equation with 2 unknown variables. So we can't solve for each of them yet. So now we got to use torque, okay? So as I said before, you can analyze torque about any point you choose on the board, okay? So the most straightforward way is to choose your point right in the middle, right? But then if you choose it in the middle, you got to analyze the torque here and the torque here, which means that you're going to have 2 unknowns as well in your torque equation. So then you would have to solve a system of equations to get to your answer. And that takes a lot of time. And we want to be as lazy as possible when we do our physics, okay? So what we do is we can analyze the torque around this point. So why do we choose this point? Well, if we choose it around this point, FA is going straight through that point, which means we don't need to include FA in our torque equation, which means that FB will be the only variable in our torque equation, which means we'll just solve for it immediately. And this just makes things a lot easier for us. So let's analyze torques around this point, okay? So that means we got MBG times 5 plus MPG times 7, because this is 7 away, equals FB times 10. All right. So as we can see here, we can just plug values in to find FB. And doing the calculations, FB equals 1103 newtons. Okay? Now I just plug this in to this equation right here. So FA will just equal to 1103. Actually, MBG plus MPG minus 1103. So let me just do that real quick. 514. As we can see here, these answers do make sense because since the point mass is closer to FB, intuitively, FB needs to exert more force to keep that point mass up rather than FA. Okay, any questions? So this is one of those examples where we had to strategically choose which point we use to find torque, which made it a lot easier for us to solve our problem. If you chose your torque around any other point, you would have still gotten the right answer, but it just takes a lot more time. So you want to be as efficient as possible. All right, another problem. I'll give you guys 5 minutes for this one. When you get your answer, please chat that to me, and I'll let you know if you're right or not. Okay, I'm going to explain this one now. So we have this problem where a sign is linked to a board and a cable holds them up. So what's the tension in the cable? That's the first part. So how do we find tension? We gotta make either a force equation or a torque equation. And since we have a hinge involved, I'm just gonna start with the torque equation. You could choose the force equation, of course, but that might be a little difficult to start with. You would just have to intuitively predict like which equation would be easier to solve. So I'm just going to guess that the torque equation will work first. And if it doesn't work, then we'll just use force, okay? So let me just do torque first. So torque around this hinge. Once again, I could choose any point, but since the hinge is given, then I'll just choose that point, okay? So we have the mass of the board going down through the center of mass, and we have the mass of the sign. Okay, so let's say the length of the board is L. And then we've got the tension force exerting a torque on the board as well. So those are all the torques in the system. So the tension torque balances out the torque by gravity, which means that T times L, that's the lever arm, times the sine of 20. Remember that torque depends on the angle. Torque equals F r sine theta, right? So we got to include that there. Equals mbg times L over 2, as it's a distance L over 2 away, plus msg times L. Now we can see that L's will cancel. T equals mbg over 2 plus msg over the sine of 20. Okay, those are all values we know. So then we can just find torque, find the tension, and tension will end up being 1,160 newtons. Okay, so now I've got the tension. Now I've got to find the force exerted by the hinge. So the hinge is going to exert a force which keeps the system in static equilibrium. Okay, so what is that force? Well, now we can make a force equation, right? Because obviously, if we choose torque over here around the force pivot on the pivot point, it's not going to do anything to help us solve for force. Okay, so we're going to do a force analysis. So first of all, we've got to split everything into components, right? The force here needs to be split into components Fy, Fx. The tension also needs to be split into components. T sine 20, T cosine 20. Okay, so let's first do forces on the x direction, horizontally. So all the horizontal forces must balance out. If we look at the diagram here, there are only two forces, Fx and T cosine 20. So this means that Fx equals T cosine 20. And we already have that. We just multiply this by the cosine of 20. We're going to get 580. Fy now. All the forces in the vertical direction must also balance out. So let's set this direction as positive, this as negative. So we're going to have Fy plus T sine 20 minus mbg minus msg equals 0. Y will equal to mbg plus msg minus T sine 20. Okay, we already have these values. We have this value as well. So Fy equals 122. Then you just use the Pythagorean theorem, right? This squared plus this squared, take the square root. The answer should be 593 newtons. All right. Are there any questions? Okay, cool. Seems like we might go a little over time today. So just like last time, if you do need to leave early, then go ahead and do so. But I don't think this week is going to extend as long as last week. It might just be like 10 minutes overtime. Okay. So I'll give you 3 minutes to do this one. Alrighty, I'm going to explain this one now. So for this problem, we have a traffic light held up by two cables. So what I'm going to do is I'm just going to do a force analysis, right? So we have, let's say this is T2, T1. So if we take the traffic light as a point mass, if we divide T1 into its components, we've got, what is this? This is T1 sine of 60, T1 cosine 60, and then for T2, we've got T2 sine of 40, T2 cosine 40, and then we've got the mass of the traffic light, mg. Okay, so the horizontal forces must balance out. This means that T1 cosine 60 equals T2 cosine 40. Vertical forces also balance out, which means T1 sine of 60 plus T2 sine 40 equals mg. Okay, two equations, two unknowns. You can solve this system for T1 and T2. So in the end, you should get T1 equals 610, T2 equals 396. Okay, any questions?
How do we know that the vertical ones, no, like the horizontal ones, aren't going in the same direction? How do we know they're in opposite directions?
Well, if they're in the same direction, then how would the system ever be in static equilibrium, right? If the forces were in the same direction, then in the horizontal direction, the traffic light would be accelerating to the right. So that's obviously not going to be possible. Okay. So this problem, so the latter problem, the example I gave in the beginning of class, is actually a very common kind of problem. So give it a shot. Give you guys 4 minutes for this one. Actually, 5 minutes for this one. Okay, so I'm going to explain this one now. We have a ladder leaning against a wall. The wall is frictionless, but the floor is not. So you want to find the minimum coefficient of static friction such that the ladder does not slip. All right. So if the static friction was not high enough, then like if it was ice or something, then the ladder would obviously slip down. Okay, so let's analyze the forces, right? To start every kind of problem, we're going to have to do a force diagram. So we've got normal force exerting up from the ground. Then we've got normal force from the wall, right? This direction, 2. Okay. So then we've got the friction, static frictional force. It's going in this direction because it wants to prevent the ladder from slipping out. So this is going to equal to N1 mu. All right. Then we've got mg going through the center. And it goes straight down. Okay, so that seems like we've got all our forces now. So let's first do a force equation. So all the forces must sum to 0. In the vertical direction, all the forces sum to 0, which means N1 equals mg. In the horizontal direction, all the forces must sum to 0. N1 mu equals N2. Okay. So now let's do some torque. Okay. So as I said in the beginning of class, we want to strategically choose our point or like our pivot point so that we will make life easier for us, right? We want to be as lazy as possible when we solve our equations. So the thing is, so for this problem, I'm going to choose a pivot point as at the bottom of the ladder. Why do I choose it there? Well, if I choose it there, observe how 2 of the forces involved are going through that point, which means that we don't even need to consider them in our torque equation, which means that we only have 2 other forces we need to consider for our torque equation. All right, if we had chosen, for example, if we didn't choose the bottom, we chose the top, then we would have 1, 2, 3 variables in our torque equation. So we want to strategically eliminate as much math we need to do in our equations. So I'm going to choose the torque from here. So then we've got 2 components of torque, which is mg going down and N2 going in this direction. Mg multiplied by L over 2, half the length. And the angle here, if we do some right triangles, the angle is 30, which means that we're going to have to multiply by the sine of 30. And this must equal to the torque supplied by N2. And using parallel lines, these are alternate interior angles, which means this is also 50. So N2 times L times the sine of 50. Or actually, no, it's not 30. This is not 30. This is actually 40 in the right triangle. All right. So now let's cancel a little bit. 1/2 mg sine 40 equals N2 sine 50. Well, since N1 equals mg, let's substitute this in here. So N2 equals mg mu. And we substitute this over here. 1/2 mg sine of 40 equals mg mu sine 50. Cancel mg's. And rearranging a little bit, we've got mu equals sine of 40 over sine of 50 times 2. Okay, so then your answer should be 0.42, I think. Yeah, 0.42. All right, any questions? So it's basically the same procedure for all of these problems. You do a torque equation, do a force equation, and yeah, so you just solve the equations. Okay? I'm going to skip this one for now because it's basically the same thing. So we got elasticity now. Well, it seems like I forgot to add a slide for types of equilibrium. So let me first change this real quick to types of equilibrium. Add a slide on that. Types of equilibrium. So we've got 2 main types of equilibrium. One of these equilibriums, so these are 2 types of static equilibrium. Okay, so one of the types is called stable equilibrium. Stable equilibrium is where if we displace the object from their from its point of static equilibrium, if we move it out, or we apply any kind of force to it, after a while, it's going to return to its original position. One example is if we have a spring. If a spring here and it's initially at rest, then it's in static equilibrium, right? If we apply a force downward, it will oscillate a little bit. It will get out of static equilibrium, but after a while, it will end up being, it will become, once again, be in static equilibrium at the exact same point. So this is an example of stable equilibrium, all right? The other type of equilibrium is unstable. Wow, what a surprise. Unstable equilibrium. This is where the object doesn't return to its original state. So one example is if we were to balance a pencil on a table and we were to apply a small force to knock it over, it would topple over and it would not become upright again. Okay? So that's an example of unstable equilibrium. Stable equilibrium is returns to original. And unstable is not return. Okay, it falls over and then that's it. All right, so those are the two types of equilibrium. And normally you're not going to really need to do any math about this. You're just going to have to identify whether a situation is stable or unstable equilibrium. Okay, so now let's move on to elasticity. Okay, elasticity. This is not really related to static equilibrium. So elasticity is basically, for this part, we're going to analyze the effect that forces have on the composition of an object. So when we see the word elasticity, we think of springs and rubber bands, right? A spring is elastic. It can stretch if we apply a force downward. It can compress if we apply the force upward. Okay? So the thing is, any object in the universe also has a certain degree of elasticity. All right? So this means that anything, even your pencil, it can stretch and compress based on what forces are applied to it. Okay? Even though it's just a tiny, tiny bit. So one example is if we have a rod hanging from the ceiling and then we hang a box to it, very heavy box, the rod will stretch a tiny, tiny bit. We'll call that delta L, change in length. Okay? Just a tiny, tiny bit. So all objects have a certain degree of elasticity. They can stretch. All right? So how do we find the specific change in length? Well, that's given by the formula. Change in length equals force L0 E A. So right now you don't know all the variables in here yet, so I'm going to explain it. So delta L is the change in length, okay? So this is how much the length is going to change. The force here is the tension force in the rod, all right? So if the rod needs to exert a tension force upward that counteracts mg, this is the force you're going to use in the equation. The greater the force, the more it's going to stretch, right? And then we've got L0, which is the original length of the rod, unstretched. Okay, its original position if there's no stretching or compressing going on. Okay, and then we've got E. What is E? You may notice that I've got a table here. This is a table of something called the Young's modulus. And the Young's modulus is E. Young's modulus is what we put in as E. And the Young's modulus is basically a measure of how stretchy an object is. Okay, as you can see, a rubber band has a very low Young's modulus, but steel has a very high Young's modulus. So what does this mean? The higher the Young's modulus is, the less stretchy an object is, right? Because steel, have you ever seen a steel rod stretching? No, right? So the smaller the Young's modulus, the more elastic it is. The bigger the Young's modulus, the less elastic it is. All right, so that's why the Young's modulus is inversely proportional to how far this object stretches. All right, and the final thing in this equation is A. A is the cross-sectional area of the object. So if we were to cut this rod right here, cut it in half, slice it in half, and we would have like a 3D view like this. This is A, okay? If we cut it in half, that's the cross-sectional area of the rod, okay? So this is basically the equation that we use to find the change in length of an object due to forces acting on it. And this equation works for both stretching and compressing, okay? For compressing, it's just that the force is in a different direction, and so is the change in length. It's going to get shorter. It's going to shrink down. Okay, so this works for both compressing and stretching. Okay, so the Young's modulus is the same for stretching and compressing. It varies a little bit, but they're generally the same. Okay, so you can use the same Young's modulus for stretching and compressing. And one way I would memorize the formula here is you can see how the letters in the formula make the word flee, right? So that's kind of like a way I would remember this formula. Just remember that there's a division sign here. Okay, are there any questions? Cool. 2 problems. These should be pretty straightforward. Actually, let's skip the bottom question. It's basically the same thing. So just do the first one. Should take around 1 minute, actually. So get your answer, please chat that to me. I'll let you know if you're right or not. All right, I'll just explain this one now. So basically the formula is change in length equals flee, FL0 over EA. So in this question, we want to find tension, which is F. So let's rearrange it a little bit. So we get F equals delta L EA over L0. All right. So we know that delta L is 0.25 centimeters, which is 0.0025. E, given 200 times 10 to the 9th. A, well, the cross-sectional area, we're just going to have to use some basic geometry here to find the area of the circle, right? It's a wire. So it's going to be pi times r squared. Divide all of that by IL0, which is 1.6. If you evaluate all of that, you get F equals 982 newtons. Okay, so I forgot to tell you guys this earlier, but you don't need to memorize the Young's moduli for each object, okay? Because that's just going to be a big waste of time. So whenever you have to do a problem with elasticity, just like this one, it's often going to give you the value, and then you just use that there. You don't have to memorize the Young's modulus at all. Okay? So let's go on. Now we've got fracture. So just like with elasticity, any object can fracture. And what does fracture mean? Fracture is basically a fancy word for breaking. Okay? So any object breaks, right? If you snap a twig in half, if you like even steel, if you stretch a piano wire too far, it will snap in half. Okay? So when we talk about fracture, we're going to talk about how forces break objects. So forces can break objects in 2 ways. One is by stretching them, which is basically tension, tensile, okay? Tensile means tension or stretching. So that's one way to break objects, by stretching them in half. And then we've got compressive, right? If we compress an object too much, it will kind of implode or something, okay? So breaking can go both ways. All right. So for breaking, for fracture, we got another table here. Okay. And the values we use for this table, we use these values to find out what's the maximum force this object can handle. And the force is actually given by F equals S times A. And S is the strength coefficient in this table. All right. And once again, you don't need to memorize these. It's just going to be given to you in the problem. So S is the strength that's given in the table. A is the cross-sectional area. All right. So this formula, so F here is the maximum force an object can handle before it breaks, or the minimum force needed to break this object. All right. So as you can see here, differently from elasticity, in elasticity we use the same Young's modulus for both stretching and compressing. But for fracture, these coefficients are actually different. As you can see, for concrete, for example, the tensile strength is a lot less than compressive strength, right? This is why concrete is used as flooring and pavement, because you compress it a lot. But concrete is rarely used as support as like a bridge, right? If you were to have a layer of concrete above 2 points as a bridge, then the concrete would stretch, right, when things go on it. And that's why you don't really see concrete built out of bridges made out of concrete. All right. So the compressive and tensile strengths are different for an object, which means that you'll have to use a different value for S depending on whether it's compressing or stretching. All right. So this is basically the formula that basically says what's the maximum force this object can handle before it breaks. Okay. Any questions? Alrighty. We'll just do one more problem with this. Once again, I'm going to skip the bottom one. I'll include this in the homework. And 1 minute for this one. It should be pretty easy. All right, I'm going to explain this one now. So the maximum force needed is given by the equation F equals S times A, where S is the strength, which is right here, and A is the cross-sectional area. So it's going to equal to 500 times 10 to the 6th multiplied by, well, the cross-sectional area is just a circle, right? And since the diameter is 0.2 centimeters, it's going to be 0.001 meters. So it's going to be pi times 0.001 squared. And if you evaluate all of this, you're going to get 1570 newtons. All right. So are there any questions? All right. So that will be it for today. Hope you guys enjoyed. And I'll send the homework and I'll see you guys next time. All right. Bye.
Bye. Thank you.
Yep. Goodbye.
Bye.